Hello to this video. In this video, I'm going to show you how to calculate the spectral irradiance for the Sun if we consider the Sun as a black body of 6000 Kelvin. This is going to help us in calculating the Shockley and quasar efficiency for black body irradiation, and so I'm going to do this as a first step of the calculations. So we have a situation as shown here. We have our semiconductor and we have the Sun that is only in part of the sky. And so as a first step, we need to calculate what is the solid angle that the Sun is observed under. Actually, for the general situation, we also need to consider that we might have a tilt of the semiconductor compared to the direction of the Sun. So this would be a solar cell that is directly oriented to the Sun. Like if we have it as shown here, we might have a certain tilt of our surface. So here we are just going to assume that we are looking at projected surfaces such that the surface, the angle theta is not considered on, because the maximum irradiance would be obtained for a surface that is directly perpendicular to the direction or to the connection to the Sun. So that theta is 0 degrees. To calculate the solid angle under which the Sun appears, we have to consider what is the diameter of the Sun and what is the distance of the Sun from Earth. And so these parameters are given here. So the diameter of the Sun is 1.39 million kilometers, and the distance of the Sun to the Earth is 149 million kilometers. And by these two parameters, we can then calculate under which angle, so how large is the surface of the Sun as visible from Earth in terms of the solid angle. And this is done by taking the surface of the Sun, so that is pi times the diameter of the Sun divided by 2, so pi times r squared. And then this needs to be divided by the distance from the Sun to the Earth squared. And so therefore this combination then gives a solid angle of 6.85 times 10 to the minus 5 steradian. So steradian, that is the solid angle unit. And if we consider a complete hemisphere, that would be 2 pi steradian. A complete circle would be 4 pi steradian. But if you have a hemisphere, it's 2 pi steradian, and then we can see now the Sun is only viewed under a solid angle of 6.85 times 10 to the minus 5 steradian. If we are considering that we want to know the geometrical correction factor for a flat solar cell, as shown here, then we have to divide the solid angle by pi, and that gives a correction factor of 2.18 times 10 to the minus 5 steradian. And this factor exactly is then the difference between the question we have the black body radiation surrounding the whole solar cell, and we have only a section. Here I'm again showing the situation where the black body radiation is surrounding the solar cell, and we already saw that this is then calculated by the Planck equation. The Planck equation, spectral irradiance, is plugged into this integral here, and then we get the incident power for this case. And the incident power for this case actually were these values I showed you previously, that at 6000 Kelvin, we have 72.1 megawatt per meter squared incident onto our solar cell if the black body radiation was coming from all sides. But now, of course, the black body radiation is only coming in a solid angle of 6.85 times 10 to the minus 5 steradian. So we have this correction factor here. This correction factor then needs to be multiplied into the equation. So the spectral irradiance for radiation everywhere compared to the spectral irradiance only at a certain part of the sky is multiplied in here. And then if we now plot the spectral irradiance multiplied with this correction factor, then we actually get the spectra that are shown here as the black lines. So the 6000 Kelvin 0 degree tilt is this black line shown here, and you can see that it somewhat exceeds the air mass 0, so the out of space radiation in this region here, but it matches quite well for wavelengths, for longer wavelengths. So in the shorter wavelength range, the difference is a bit larger than in the longer wavelength range, it matches quite well. So this black curve I calculated by multiplying this correction factor with the spectral irradiance at a temperature of 6000 Kelvin. And the correction factor is again given here. And then for comparison, I also plotted a black body at 5800 Kelvin that has the same size and distance to the Earth as the Sun. And then we would expect to have at air mass 0 the dashed line here. So you can see the dashed line agrees somewhat better with the AM0 line. And if you compare the absolute values, the AM0 spectrum has an absolute power of 1350 watts per meter squared. And at 5800 Kelvin, a black body has 1370 watt per meter squared. So actually, this dashed curve is closer in terms of integrated intensity than the 6000 Kelvin curve is, which would correspond to 1570 watt per meter squared. So we can see from this that we can model the solar radiation by assuming a black body radiator, and depending on which source you look at, different values will be taken. So Shockley and Quasar used 6000 Kelvin. You can of course also go ahead and try to match a certain value here in terms of the total power to match it better to your spectrum. So then you might, for example, use 5800 Kelvin. 5770 Kelvin is also quite typical as a number to use. But somewhere in that range you obtain a spectrum, a black body spectrum that resembles the solar spectrum quite well. So we can calculate now either with the black body spectrum what the efficiency is, or we can use the experimental values which are more exactly representing what is reached on Earth. So I put this in here because Shockley and Quasar calculated everything with a black body radiation, so that if you want to compare the values to the Shockley and Quasar original paper, it's useful to have these spectral irradiance values. And I will also continue my calculation using these values. Thanks for watching.